Hi-oh! Now it's time to talk about free fall. We're going to specifically talk about it conceptually today, and the next lecture we'll throw in some math. In order to talk about this, we really got to talk about what causes things to accelerate. And our first statement here is forces cause things to accelerate. Go ahead and push on something. Push your book or your paper. You're applying a force. What does it do? It goes from 0 to something. It has a change in velocity. And if you remember, acceleration is a change in velocity for some time. So forces cause acceleration. And I think it's just safe to say that gravity is in fact a force. Gravity is pretty consistent here on Earth. And because of that, the force that gravity pulls with, or I should actually say, the force at which gravity applies tends to accelerate things with a very known value. And we call this value little g. So it's a symbol we use. When you see that, that's a constant. On Earth, it's always -10. Negative, of course, means it's down. If it was positive, we'd be flying off the Earth. So the acceleration caused by gravity is always down. And it doesn't matter what you're doing. You're always being pulled downward and therefore accelerated downward. So if we drop an object, let's say a feather, guess what? It's going to accelerate at a rate of -10. So it's going to change its velocity by that much downward every second. Hammer, same thing. But wait a minute, hammer, feather? Really? If I drop those, they're going to change their velocity by 10 meters per second in the first second, 10 meters per second in the second, and so forth down the road? Really? Even if I use a book or a piece of paper? Come on. No, really. They'll all fall at the same rate. I know you don't believe me. That's because you're thinking about air. Get rid of the air and it happens. So take your last breath. No longer will we have any air until later on in the course. So make sure it's a good one. So how can we prove this? It's hard to see because you live in an ocean of air. Well, watch this video. It's of an astronaut on the moon dropping both a hammer and a feather. And guess what? There is no air on the moon. You have to realize the picture quality is not all that great simply because we're using technology from the 1960s.
Everything on the moon weighs less than it does back home. Things fall more slowly, even though there's almost no atmosphere on the moon. But still, all bodies, even a hammer and a feather, fall.
Well, hopefully you liked the video. And if you look at an object, let's talk about those objects falling. What would it look like if you throw it up in the air, the hammer or the feather? It's going to look identically. Let's talk about an object moving downward. Right? It's going to pick up speed. Start at 0 meters per second, and then it's going 10 meters per second. Right? It's changing its velocity by 10 every time. Next one's 20 meters per second, 30, 40, 50. It's going to speed up. And if it's speeding up, it's going to cover more distance each time. However, when we throw it up, gravity is pulling things down, which means the acceleration is downward. So as we throw something up, it's going to lose 10 meters per second each time. So if we threw this up at 50 meters per second, in 1 second time, that's what these lines represent, 1 second of time, it's going to be going 40. And then another second later, 30, 20, 10, and back to 0. So the path is going to look something like this. So if you look at the patterns, Notice the velocities and the accelerations. The accelerations are the same in each case. The Earth is always trying to accelerate things downward. But when you throw something up, the velocity is upward. Doesn't mean it's speeding up. It just means the velocity is upward. Notice these are in opposite direction. They're slowing down. As it comes down, it is going to speed up. The velocity is down, so's the acceleration. They're both doing the same thing. They're reinforcing each other. Let's apply this to a woman hitting a volleyball. We talk about the speed. Let's say her velocity that she hits the ball with, in other words, it leaves her hand at 30 meters per second. We know little g, negative means it's being down, right? 10 meters per second. So it's going to lose that much velocity every second, right? Acceleration, little g is acceleration. It's a change in velocity over time. It changes by 10 meters per second every second. So 1 second later, each point represents 1 second in time. It lost 10, so now it's going 20 meters per second. Another second, it lost 10, so it's going 10 meters per second. And now 0 meters per second. Is gravity still pulling at point D? You bet it is. Still trying to be accelerated downward. In other words, acceleration caused by gravity at D is still negative 10. At C, it's still negative 10. It's negative 10 everywhere, even on the way down. So on the way down, it's going to start increasing its speed. It's going to be going 10 meters per second, then 20 meters per second, 30 meters per second. Look at that. It's going just as fast on the way down as it was on the way up. Those are speeds. What's the difference between speed and velocity? If you said direction, you're correct. The direction is up. Up is positive. So velocity-wise, all of these are positive. On the other side, down is negative. These would be negative. These would be negative velocities. So what about time? Remember, each position represents 1 second in time. How long does it take for the ball to get to its apex at D? Well, each dot represents 1 second in time. It lost 10 meters per second, each one. So 1 second. So here's 1 second, 2 seconds, 3 seconds to get to D. What about to come all the way back down? 4 seconds, 5 seconds, 6 seconds. So it's a 6-second round trip. So let's review. Each position of these will represent 1 second in time. The speed is going to change by 10 meters per second, whether it's going up or down. On the way up, it's losing. On the way down, it's gaining. Think about it. Let something go from your hand and it speeds up as it hits the ground. Throw it up in the air and watch it. It will slow down. Gravity is still accelerating things regardless where it is in its path. So let me ask you, what if instead of using this ball, we use a gun? You fire a bullet in the air straight up. Let's say it leaves. I don't know how much a bullet moves from a gun, but let's say it leaves at 300 meters per second. It leaves. So here's our gun. Straight up. Let's say it's 100 meters per second. How fast is it going to be going when it comes down? Hopefully you said 100 meters per second. So watch this video from The Simpsons and see for yourself.
So, in the amber gloaming of this September afternoon, Shelbyville has the bases loaded. But the Isotots only need 1 out to win the championship and get that pizza party at Luigi's. Luigi's, they deliver on flavor, but not to your house.
Damas y caballeros, if the Isotots win, please do not fire your guns in the air. The bullets will come down and kill my sister.